Today we're going to do 5-1 perpendicular and angle bisectors. Let's start it off by looking at an image. Now we see an image of a town, and of course it's a made-up town, but what I want to do is let's try to find, we see the cemetery here and the post office off to the right. What we want to do is find two locations that are today we're going to talk about 5-1 perpendicular and angle bisectors. Let's start off by looking at an image. We see an image of a town. It's a made-up town, but what we want to do to start off with is, if you notice the city library off to the left and the post office slightly off to the right. What we want to do is let's start off and let's try to find a building in this town that is the same distance from the library to the post office. We could probably mark on these on the library. Let's go blue, and post office we can also do blue. We want to find two buildings, or we want to find buildings that are the same distance away from these two places. If we're looking at our map, you're probably not going to be saying something such as the community center way down on the bottom left. Also, maybe the city high school on the right. You're not going to be talking about. They're too close to either side. So one that you might automatically notice is the City Hall. City Hall seems to be right in the middle, and I would agree with you. City Hall would be a good place to start, but we're certainly not going to finish there. So we see the City Hall is right in the middle. You might also want to say, if you're looking, that the City Court could be in the middle. Could be the same distance from our two blue dots. And I say that just because, although it's not directly in the middle, if you see it's slightly offset and to the bottom, the distance that we would need to travel appears to be exactly the same. And we could keep on going down, all the way down this map. Same with the fire station and even the city park, at least parts of the city park, would be the same distance away from our blue dots. Saying the same distance away is kind of annoying. We have a word for that. We have the word equidistant, which is the same distance from two objects. So all of our red dots are equidistant to the blue dots. Also, if you notice, and we're leading into a theorem here, if you notice, we could draw a line directly down our red dots, and let's draw a line to our blue dots. If you notice our line going down, down the line of the red equidistant locations, I'm going to claim that we're laying on the perpendicular bisector. As you notice, we have a right angle here, a perpendicular bisector. That's a word that we heard earlier. Let's see what that means as a reminder. Perpendicular bisector. And perpendicular bisector cuts a line segment in two congruent parts, and it forms a right angle with the segment. And as you notice, our equidistant red dots seem to do that. They seem to cut our the distance from the blue dots in half, and it's at a right angle. And we have a few theorems that deal with perpendicular bisectors. We have two theorems that deal with perpendicular bisectors. The first of which is theorem 5-1-1, and it's called the Perpendicular Bisector Theorem. What it says is that if a point is on the perpendicular bisector, and again that's a word that we already know, of a segment, then it is equidistant from the endpoints of the segment. So what exactly does that mean? let's draw a picture and see if we can better see what that looks like. If we have 2 points, let's say A and B. It says that we do have a segment, and so connecting these 2 points, let's draw a segment. And let's see, our perpendicular bisector theorem says that if a point is on the perpendicular bisector. So let's go ahead and draw the perpendicular bisector. Remember, it cuts it exactly in half. Seems to be right about there. Let's continue that down. There's our perpendicular bisector. We can call it anything. Let's call it line L. It's bisecting, and so we need to make sure that's perpendicular for one, and it's bisecting the segment AB. It's cutting it in half. What our theorem says is that we can choose any point on this blue line. Choose any point on the line L, and it will be the same distance to A that it is to B. An example of that would be choose a point, let's say, right there. It's on our blue line. What our theorem tells us is that if we were to make a line from A to our red dot, and also from our red dot to B, our theorem tells us that these line segments are exactly the same length. And we could do that for any points, again, on this blue line. Let's do one more. How about a green dot? Green dot down here. What our theorem tells us is that if we were to draw a line segment from this green dot to the point B and our green dot to point A, these two line segments are going to be exactly the same length. And the reason why is because this blue line is the perpendicular bisector. That's why this is true, and that is exactly what our theorem is telling us. And then let's look at our second theorem now. Our second theorem is called theorem 5-1-2, converse of the perpendicular bisector theorem. Before we actually hop into exactly what this one says, let's remember this word, converse. What does converse mean? Remember that converse means the exact opposite. That's kind of a shorthand definition, but it means the exact opposite. So the converse of the perpendicular bisector theorem, the exact opposite of the perpendicular bisector theorem. What that would mean then is exactly the opposite of earlier. And so let's actually see exactly what it says now. This theorem says that if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector. Remember, this is the exact opposite of theorem 5-1-1. The reason why is that what we knew with 5-1-1 is that it is on the perpendicular bisector. This one, what we are given, what we know, is that it's equidistant from the endpoints. So looking at that in a drawing, that would tell us that if we have 2 points, let's start off just like we did before, 2 points A and B. We can draw a line segment between these 2 points. And let's just choose a random point. Let's choose maybe a point up here. You can call it point C. But if I tell you, if you know that if you were to draw a segment from A to C and from C to B, and that these two green segments are congruent, our converse, our 5-1-2, tells us that then if you were to drop a line straight down, this red line is the perpendicular bisector. That's the exact opposite of our other theorem. The other theorem gives us the perpendicular bisector. This one tells us that, okay, our point must be on it. Those are the two key differences, so understand the differences. So how do we actually use the perpendicular bisector theorem, or the converse of the perpendicular bisector theorem? If you see, we have a triangle here with a perpendicular line coming down, our perpendicular line being the line GF. We know it's perpendicular because of this right angle here. But now what we are told that we are told in this triangle that the line GF is the perpendicular bisector of the line segment DE, and EG is equal to 14.6. Notice there's no line. There's no line up here. What does that mean? The length of now let's label our picture here, our diagram. Makes it clear that GE is the perpendicular bisector. Well, we see that GE is perpendicular, but because it's a bisector, let's label it as two congruent segments of DE, and the length of EG is 14.6. Okay, we want to find the length of DG then. So we see that the length from E to G is 14.6. Isn't G on the perpendicular bisector? You can label that for your notes as G is on the perpendicular bisector. Because G is on the perpendicular bisector, we can use our theorem 5-1-1, our perpendicular bisector theorem. And why is it not the converse? Reason why it's not the converse is because we know that G is on the perpendicular bisector. So because we can use our theorem, we can say for maybe an answer is that the perpendicular bisector theorem tells us that the length of GE will be congruent to the length of DG. We know these two lengths will be the exact same. So therefore it's easy to see that DG is going to be 14.6. DG is equal to 14.6. Let's do one more example. Let's flip it now, and maybe we'll use the converse, I believe. Alright, our new example here tells us that DE, remember that we do not have a bar over DE. This means the length of. The length of DE, same with the length of DG and the length of EG. So we want to find the length of EF. First things first, and let's go ahead and label our diagram. Labeling our diagram, DE, the total length is going to be 20.8. DG is equal to 36.4, and EG is equal to 36.4 as well. Well, if we look, 36.4 and 36.4 must be congruent, aren't they? They're the same length, so we have two segments being congruent. Once two segments are congruent, do we know anything about a perpendicular bisector? Go ahead and read everything we know. Does it say anything about the perpendicular bisector? No. It says nothing about the perpendicular bisector. And so it's important to know that we cannot use the perpendicular bisector theorem. We can't use that because we don't know anything about perpendicular bisectors yet. What we do know, though, is that we have two congruent segments. So we're going to use the converse of the perpendicular bisector theorem. And this is because we have two congruent segments. Oops, and I forgot a apostrophe or a parentheses there. So we're going to use the converse of the perpendicular bisector theorem, which tells us that because these two sides are congruent, we can say that G must be on the perpendicular bisector. This was not given to us. We got this because of the converse. Because it's on the perpendicular bisector, then, we know that the line GF is the perpendicular bisector. Meaning that what it does is it cuts the line segment DE into two congruent segments. Therefore, we are looking for EF. Isn't EF then? You see EF here, but you have another segment right to the left of it that they're congruent and they add up to 20.8. So what we can do is we can take 20.8 and divide this by 2, which you'll see is 10.4. And therefore you see that EF is equal to 10.4, and now we are done. And we did this all by using the converse of the perpendicular bisector theorem.